Hello, everyone. Welcome back to grade 11 university level physics. Here we are, lesson 3 of unit 2. Let's talk about friction and why things get slowed down. Basically, friction affects everything. There's nothing that's no friction unless you're talking about very strange things like superfluid helium at 4 degrees, 2.7 degrees Kelvin, but whatever. Almost everything has friction. There's some sort of force that slows things down. There's some sort of inefficiency in systems. But we're going to talk mostly about simple mechanical friction. So friction is a force that opposes motion by generating a force in the opposite direction of the object's motion. So that can be, sliding friction, like when you push something across a table and it resists that motion. You push something, let go, and it's going to stop pretty much right away, unless it's a rolling object. Rolling objects have rolling friction. There's also friction there, much, much, much less. Or fluid friction, which could be air resistance. It could be trying to run through water. It's difficult because you're pushing all that dense liquid out of the way. That slows you down. But air, even though it's not very much resistance if you're moving slowly, but if you put your hand out of your car window when you're traveling down the highway at 80 kilometers an hour, you can definitely feel that resistance. Or if you're re-entering the atmosphere, you can feel that resistance by heating up to incredibly high temperatures. When objects are re-entering the atmosphere, they're re-entering the atmosphere at thousands of kilometers an hour, and at that speed, those air molecules, they can't get out of the way fast enough. And when you push them out of the way that fast, you heat them up to incredibly high temperatures. And you have to design your rocket ship or spaceship or whatever it is to be able to deal with that massive air resistance. But let's talk about sliding friction. And we're going to analyze sliding friction using this formula that says that the magnitude of the force of friction is proportional to the normal force acting on the object by the surface it's on. So remember, we talked about normal force. If an object is sitting on a desk, gravity is pushing it down, but the normal force is counterbalancing that force of gravity. And its proportionality constant is what we call the coefficient of friction. And that coefficient of friction depends on the material. So, for example, if you're trying to push, I'm not sure, push a puck across a, a paved road or even a gravel road, there's going to be a lot of friction. So the coefficient of friction in that case, this mu, just this letter here, looks like a U, but it's actually a Greek lowercase m. And you draw it just like you would draw U, but instead of starting at the top where you would draw a U, you start at the bottom and you pull up and then you get a U. Okay, and that's your line. So it goes underneath the line a little bit. This is called, whoops, I'm not pressing the eraser. This is called a mu, lowercase Greek m. So this we call the coefficient of friction. And typically you'll be given that or you'll be asked to find that or something like that. So that's a number, it's a numerical quantity, it's unitless. Notice that the equation here has newtons and newtons as our units on both sides. So for this to work, there's no units on mu. It's a coefficient, really. It's just a proportionality coefficient that allows us to make this equation work. And really, this is just linear, right? Y equals mx. It's like a slope, that mu. You can analyze friction in much higher orders. You can have to the force, the normal force squared, cubed, and so on and so forth. Make this big polynomial, but we're just going to go a very simple linear expression here. Okay. Now, careful here. So why it's not equal to the force of gravity acting on the object is because you can actually, let's say you have a textbook and there's a force of friction if I just push it across the table. But if I push down on that textbook with my hand, if I'm pushing down on that textbook, I am increasing the normal force because there's the force of gravity pulling it down, but there's also my hand pushing it down. I'm increasing that force downwards, so necessarily the normal force will have to increase, and when that normal force increases, it's harder to push across the table. When you're pushing down on something, we are increasing the friction. That's why it's proportional to the normal force. Also, if you have an object and you are able to lift it, not actually lift it, but you're able to pull up on it, reducing the normal force. Let's say it's a very heavy object, but you're able to lift it a little bit, not actually get it off the ground, but you're able to push it, pull it up with some force, thereby reducing the normal force. That will also decrease the friction. You'll see this when we get to an example. Okay, so let's do a simple example here. We have a 170 gram puck. Okay, and it's going to slide across some ice on a rink at 19 meters a second forward. It's going to hit a 5-meter rough patch. So there's a 5-meter patch of ice that's rougher than the regular sliding ice. The coefficient between the puck and the rough ice is 1.56. Notice again that that's unitless. Calculate the velocity of the puck as it leaves the rough ice. So for us to calculate a new velocity from an old velocity, we're going to have to necessarily get an acceleration. So what can we do? How can we start this problem? Well, let's see if we can figure out a force of friction. And let's put all this into a nice free body diagram. So typically, first thing you want to do when any sort of force problem like this, draw a picture. Okay, so again, free body diagram. The picture is just a box. In this case, a puck, when you look at it from the side, will look like a little rectangle. But again, that shape of the diagram doesn't matter. So what forces are acting on this? We have the force of gravity pushing down, right? But because the puck isn't levitating or going down into the ice, it has a normal force to counteract that. And if it was just like this, then the object would not change speed. But it's telling us that it's slowing down. So we have to put a friction force. I'm going to add to this. Let's say the velocity is in this direction. Okay, that's an arrow. Okay, velocity is that direction. So the friction will be in the opposite direction. And now in these free body diagrams, don't worry too much about the size of the arrows. I drew this force of friction smaller, right? The scale does matter in a sense, but as long as it sort of fits, right? As long as, like in this case, for example, the normal force and the force of gravity, those arrows have to be the same length. The exact length they are doesn't really matter as long as they're the same length. Okay, and as long as they're in the right directions, that's critical. The right direction is critical. The magnitude, the length, not so much. Okay, so what do we know? We have a mass, which we can convert to kilograms, 0.170 kilograms. We have an initial velocity vector, 19 meters per second forwards. And we know that it's going to have a displacement across the rough ice of 5.1 meters forward. It's going to displace in the same direction as it travels, right? And we know that the coefficient of friction is 1.56. All right. So let's start off with our F equals ma equation. Now, notice I'm not putting vector signs on this. Things do get a little bit complicated in friction problems because, and notice if we go back to my original formula for friction, I left it as a scalar equation because normal force and force of friction are not collinear. You cannot put a vector sign. Let's go back actually, all the way back here. In this expression, these are not vectors because the force of friction is not in the same direction as the normal force. This is just saying the magnitude of the force of friction is equal to mu times the magnitude of the normal force. Okay, sorry about the noise in the background. So the net force is mass times acceleration, right? We know that the net force from our picture, right? We can see in this picture, our net force is going to be equal to just the unbalanced bit, which in this case is the force of friction. So in the case that we can rewrite this expression in saying the force of friction is the mass times the acceleration, and we know that that force of friction is equal to mu Fn. I've just flipped the equation around just to make things a little bit clearer, because really I'm trying to get A by itself. So I just flipped it around. The normal force in this case is equal to the force of gravity. In this case, just looking at our picture, we know that there's nothing pushing down or pulling up. So the normal force is equal to the force of the weight of it pulling down. And that's going to be mass times gravity. And look at this beautiful equation here. What do you notice about this equation? M's, they cancel. I can just say that the acceleration is mu times g. Isn't that beautiful? The m's are on both sides of the equation. Canceling just means dividing both sides by m. Really, we're just making it 1. We're not actually canceling. Canceling sounds like you're just making it disappear. You're making it disappear by changing it into a 1, right? Because we're dividing both sides by m. Okay, and we end up with A equals mu g. So we really didn't care that the puck was 170 grams. It didn't make any difference. It wouldn't have mattered what the weight is of the object. It cancels out in the expression. That's awesome. Anyways, so we plug in our numbers, 1.56 times 9.81, and we end up, with 15.3 meters per second squared. Now we go back to our kinematic expressions here, and we can just, I think my volume is a bit loud, probably clipping a little bit, sorry about that. So then I can just go v squared, v2 squared equals v1 squared plus 2a delta d. Okay, notice I haven't put vectors on these. We'll just put a vector on the end. At the end, we know that the acceleration is negative, right? Because it's slowing it down. We know the initial. Well, here I'll plug in. Where am I? When I plug in the numbers to this expression here, I know that 19 was forward, so that's positive, and I know that the acceleration was 15.3 negative because it's resisting the motion, right? Because friction is in the opposite direction of its motion. The displacement is still positive, right? Because we know, think about what it's doing here. Here's my object to begin with, and here's my object afterwards. It's going to travel from here to here. It's going to start off with V1, and it's going to end up, stop moving screen, V2. Okay? So it's going to be slowing down, so acceleration has to be in the opposite direction of its displacement. Right, displaced this way, acceleration is the opposite direction. This is positive, acceleration is negative, and I can put all the velocities as positive because it's going to still be, unless the rough patch is so long that it stops. But let's see if that actually happens. We're going to plug in our numbers, and we get 14.3 meters a second. And now we can put the vector sign on this. Because this ended up being a positive number, I can round it to 2 significant digits because 19 had 2 significant digits, 5.1 had 2 significant digits. So I can round this to 14 meters per second forward. Right, it slowed from 19 to 14 meters a second. And we can put a final therefore statement on it, and we're good to go. Okay, so just be careful with your vector signs. I recommend not putting vector signs on any of these friction problems, and just keeping in mind when is it positive and when is it negative. Use the positive and negatives to demonstrate your signs. Okay, now that's going to become a lot more difficult in the next example. Okay, because we're now going to have, let's say we have a crate. It weighs 400 newtons. That's a force. Okay, so that's the force of gravity pulling down. It's 400 newtons on it. It's on a horizontal sidewalk and it's moving at constant speed. And it's being pulled by a rope that makes an angle of 45 degrees with the sidewalk. A force of 150 newtons is applied to the rope. What is the coefficient of sliding friction? Okay, so let's think about this. Again, constant speed. Constant speed means that there has to be a net force of 0. All the forces acting on this in the x direction and the y direction have to cancel. So let's start with the y direction. Okay, so I know that the force of gravity is pulling downwards. Now, the rope is not up, down, left, or right. It's at 45 degrees. I've just arbitrarily chosen that to be left. Could have been right. It doesn't matter. I'm going to pull it to the left. Now, this vector is not resolved in or broken down into x and y components. We need to do that. We need to treat this situation like a two-dimensional problem, and we can only deal with vectors that are in the same direction. So let's break it up into an FAY and an FAX. Right? And that angle here, that's going to be our 45-degree angle. Okay, so now if I look at this force of gravity, that's pulling down and FAY is pulling up. The normal force can't be equal to FG in this case. The normal force has to be equal to the difference between the force of gravity and the y component of the applied force. Or another way of saying it, the normal force here plus the y component here, these two red lines, these two red vertical lines going up, have to be the same length as the big red line going down. These two, the sum of FAY and FN has to be equal to FG. These two vectors are not the same length. Okay, so in that case, the y component of, in the y direction, our forces are balanced. So the net force is 0 in the y direction. In the x direction, we're going to have to say that the force of friction is equal to the x component of our applied force, because these two lines, the two blue lines, have to be the same length. Right? All the red lines have to add up to 0, and all the blue lines have to add up to 0. This is why drawing a picture is so important. Okay, make sure you draw a picture. It helps you put together all the ideas of what's happening. And now that we have our picture, we can come up with a mathematical expression. So in the blue direction, the x direction, the friction force, now notice these are not vectors here. These are vectors in our picture. Whenever you draw them in our picture, you put vector signs on them. Whenever I've removed the vector signs for ease of worrying about directions like we talked about already. Okay, so I've removed the vector signs, these are just scalar quantities. Otherwise, I would have to put, if I put vector signs on here, I would have had to put a negative sign on one of them to show that they're in the opposite direction. Right, because one's facing left, one's facing right, they would be opposite. If I get rid of the vector signs, I can say that they're equal because the magnitude, their lengths are the same. Okay, and for the y direction, the red direction, the force of gravity has to be equal to the y component of the applied force and the normal force. So these two lines pointing upwards have to be equal to the big line pointing down. Okay, then I can rewrite the force of friction as mu Fn, and the x component is going to be the cosine of the angle multiplied by the hypotenuse, which is Fa. And same thing happens except for the sine. Really, sine of 45 is equal to the cosine of 45, but we'll just leave it. And now I have two expressions here. I need what I'm looking for. I'm looking for the coefficient of friction. So that's my unknown is mu. But the normal force is also unknown. However, I have two equations, two unknowns. I can solve it. Remember substitution? If I rearrange this red equation in terms of Fn, I can now substitute this expression in for Fn. So my blue equation, I had an Fn, a normal force. My red equation, I had a normal force. I solved using the red equation, I solved for it. I brought the Fa sine theta over the other side, it became negative. And then I just take all this stuff and I replace it over here for Fn. Okay, if you get stuck on that, just go back and watch it again. Now rewriting it, this is the same equation without the reds and blues. I just rewrote it. Now I need mu by itself, so let's divide both sides by the whole bracket, and we come up with an expression for our coefficient of friction. And we just have to plug in our numbers, and we ended up with 0.36 as our coefficient of friction. right? The applied force was 150, the angle was 45, force of gravity was 400. That should be 150 here. Sorry, that should be a 1 there. Let me just check quickly. Yeah, sorry, that was just a little typo there. That should be a 150 there. It still works out to 0.36. Okay, and then we can put a final therefore statement, and we're done. Okay, so this is a little bit more complicated where we have to resolve these vectors into x and y directions and go from there. But it's pretty straightforward once let's go back here. Once we end up with these two expressions, this is the hard part. This is the physics part. The rest of it's all just algebra. Doing all this stuff, this is just algebraic manipulation of stuff. Okay, but it's these two expressions that are the heart of the problem. And to get them, we draw a picture. So please make sure you draw pictures all the time. Okay? All right. So we finished that problem. Sorry about the typo there. And so now we can work on some problems here. So attached is some friction problems. 1 to 6, I think, are one-dimensional, pretty straightforward problems. 7, 8, 9 are these two-dimensional problems. Okay, again, all the solutions are posted. And awesome. I hope you guys are having fun. And I'll be seeing you later. Again, good luck and stay safe.